You're welcome to day 21 of 50 days of tutelage. In today's class, I will be talking about stoichiometry. And what is stoichiometry? It is the quantitative study of relationship that exists between reactant and product. So during a reaction, there are things that we call the reactant, and then there are some things that we call the product. The reactant are the things that are being used up, while the product are the things that are being formed in the process. So this relationship, such that you have A plus B to give C, in this situation, we have A plus B as the reactant. So A plus B, they are the reactants, and C is the product. So the quantitative study of this whole process is what is called stoichiometry. So how much of this is being used, and then how much of this is being formed. That's exactly what stoichiometry is all about. So which implies that for us to be able to do proper stoichiometry, one of the first things we need to know is to how balance equation properly. And we have been able to do justice to that in our previous classes. You can always see the link to follow if you were not in that class. You can see the link to follow to check the class out. Now, so let's go right into it. So the concept of stoichiometry, actually, you can be given a lot of information about a given reactant or even a product, and you are asked to find other things in the system of equation. So what happens is that, for instance, these are the things that you can be given. You can be given mass, you can be given volume, you can be given mole, you can be given so many things that are related in this place. You can even be given concentration. You can also be given concentration, and so on like that. So different quantities, different type of things that you can be given: mass, volume, mole, concentration. But here's the thing: the only thing we use all the time, is mole. We always want to use mole for comparison. So that is why for every time we are dealing with a stoichiometric problem, we always want to compare them based on mole ratio. However, the only time you can decide to use the volume, that is, you can use volume for comparison, is when everything that you are dealing with here, they are all gases. So that is the first thing you should take note about stoichiometry. So no matter what the information that you are given in a problem, if you're given mass, if you're given concentration, or just any information, you don't jump ahead and say you want to look for the mole ratio. For instance, now let's say A plus B is C. Now let's say you were given the mass of A to be 2 grams, and they say completely this mass of A, 2 gram, was used to react with 3 grams of these, and then so how much gram of C will be formed? Now, in this situation, there's something we call limiting reactants and excess reactants, which I'm going to explain very soon in this video. So let's assume that you assume that this is the limiting reactant now, and the ratio is ratio 1 to 1. So therefore, you say 2 gram of this one has been formed. Now, in that situation, you are going to be wrong because mass is what you are using as comparison. So, which leads me into what exactly is all this comparison, mole comparison, and the like. How do we do ratio and all of that? So, the first thing is that you need to always write what we call a balanced chemical equation. For example, in the reaction to form water, when you have reaction of hydrogen gas plus oxygen gas to give H2O. The balanced chemical equation in this place, you have 2 at the back of H2 here, and you have 2 at the back of H2O. This is a balanced chemical equation. So what can we say about their ratio? Their mole ratio is 2 ratio 1 ratio 2. So what you notice here is that these guys, they are in 2 ratio 1 ratio 2. So hydrogen, whenever you have 2 of hydrogen, you will need half of that amount for oxygen. Whenever you have 1 of oxygen, you need double of that for water to be formed. So, and this thing you can be given in terms of mass. So for instance, if I had given you that um, 3 grams of hydrogen gas reacted with, let's say, in this situation now, 4 grams of oxygen. So what is the mass of water that was formed? Now you might be tempted to say, oh, 3 gram plus 4 gram and all of those things. Or you might be tempted to say this is 2 ratio 1. So if I have 3 of these, that means that 1.5 gram of oxygen will be needed, because if it is 2:1, that means that double half. So when there is 2 here, there will be 1. So when there is 3 here, just find the half. That means that 1.5 gram of oxygen will be needed. And in this case, I have 4 gram of oxygen. Then what do I need? It shows that I need whatever number this one is, you double it. So if there's 4 gram of this, I need 8 gram of this. So that implies that in this place we have oxygen in excess, because what do we need exactly for oxygen? We need 1.5 gram, but what do we have? 4 grams. If we were to consider oxygen first, what do we need? We need 8 grams. But how much of hydrogen gas do we have? 3 grams, and therefore we have it as a limiting whatever. But you will be very, very wrong, because you are dealing with it in terms of mass. So how do we now go about it? So I'm going to teach you the concept of limiting and excess reactants properly now, using the right thing. So what you use is always supposed to be moles. So let's rewrite this now. So you were given 3 grams of hydrogen and 4 grams of oxygen. So the first thing you need to do is find the number of moles of hydrogen gas. And that will be mass divided by the molar mass. So what's the mass of hydrogen gas that was given? That's 3. And then what's the molar mass of hydrogen gas? That's 2. Why is it 2? It's 2 because we have hydrogen is 1, so we have diatomic, so that's multiplied by 2. So in that case, you have 1.5 mole. So 1.5 mole. Then number of moles of oxygen gas, still also mass divided by molar mass. So what's the mass that was given? 4. Now oxygen itself is 16, so maybe since it is diatomic, that will be 32. So 4 divided by 32, 4 divided by 32, that is 0.125. 0.125 mole. So in that situation, I have. So let's now determine which one is the limiting reactant and which one is the excess reactant. So it's very easy. What you need to do is that you blindly pick one of these two and assume that the other one was not given. So just follow this step one after the other. Blindly pick one of these and assume that the other one was not given. So to do that, I'm going to pick the first guy here, hydrogen gas. So how much of hydrogen gas do I have? 1.5 mole. So I'm going to write here number of mole of hydrogen gas ratio number of mole of oxygen gas. Based on the equation, we have 2:1. And blindly, I want to assume that only hydrogen gas was given. So that is 1.5 mole. And oxygen gas was not given. So this is going to be 1.5 ratio. Now, I'm going to make this one X because, like I said, I've assumed that oxygen gas was not given. So in that case, I'm not going to cross multiply here, and I'm going to solve for the number of moles of oxygen. So that will be 2x equals 1.5. And that implies that x equals 1.5 divided by 2. So what is 1.5 divided by 2? That is 0.75. Now, do you know what this implies? This implies that for the given number of mole of hydrogen gas, the exact number of mole of oxygen gas that I need is 0.75 mole. But the question is, I need to go and check how much oxygen did I have in the first place? How much of oxygen was I given in the first place? Compared with this 0.75 mole that I actually need. So now I have 0.125 mole of oxygen. Since I have 0.125 mole of oxygen, but what do I need? I need 0.75 mole of oxygen. Now, that implies that I have lesser because what I have is 0.125. This is what I have. And it is less than 0.75. This is what I need. So in that case, what I have is less than what I need. Then this is going to be my limiting reactant. And in fact, it is going to be the one to determine the extent of the reaction. So which implies that whatever thing I'm going to be doing from now on, this limiting reactant is going to be the tool I'm going to be using for any other thing I want to solve for in the entire process, because it determines the extent of the reaction. So now going back now, what is the mass of water that is given in that place? So all I have to do is to do comparison again. Mole ratio, so number of mole of oxygen gas ratio number of mole of water formed, it is 1:2 from the equation. So you can see we have 1:2 here. So what's the number of mole of oxygen gas that I have? 0.125. Please make sure you don't make mistake and use 0.75. 0.75 is just the expected, but that's not what you have. So you have 0.125, which is going to be 0.125 ratio x. If you do this very well, solve it the same way, x is going to be 0.25. 0.25. Let's confirm that. Yeah, 0.25. Now that you have the number of mole of water, so number of mole of H2O equals mass of H2O divided by the molar mass of H2O, or you can just say relative molecular mass. Now, in this case now, that implies that number of mole of H2O is 0.25, which is equal to mass of H2O is what we're looking for. What's the molar mass? H2O, H is 1, so 1 times 2 plus O is 16, so everything is 18. So you have 18 here. Therefore, mass of water formed will be 18 times 0.25. 18 times 0.25. And that would be 4.5 grams. 4.5 grams. So that implies that when you are given 3 grams of hydrogen gas, 4 grams of oxygen gas, what you are going to get is going to be 4.5 grams of water. 4.5 grams of water. As we have said, hydrogen gas is in excess. Hydrogen gas is in excess. So therefore, this whole system, we have total mass here is 7 grams. Total mass here is 4.5 grams. That implies that 7 minus 4.5, I think that should be 2.5. 7 minus 4.5. So that means that 2.5 gram of a quantity was not used in the entire process. And what quantity is that? The quantity that was in excess. That would be the hydrogen gas. So if you look at the number of mole of hydrogen gas that would have been used in this process, that would have been double of this, which is 0.25. So if you do the calculation, that is, you can do the comparison now. This is the limiting reactant and it is 0.125. So if this is 1, then double of it is what will be required for hydrogen gas. That means that you have 0.25 equals mass over that of water, that's 2. So if you multiply this, mass of water used is going to be 0.5 grams. So I'm out of the 3 gram of hydrogen gas, only 0.5 gram was used in the process. So the 2.5 gram will still remain as hydrogen gas in that place. In fact, that is why sometimes you can be doing the calculation and they will ask you about a residual gas. A residual gas. Now, in that situation, okay, by the way, this is a gas, and this is liquid. So once you are asked about residual gas, it's talking about after the reaction had taken place, all the gas that are present in the chamber or in the reaction when the reaction has been done. And that would include your excess and also whatever was formed in the process. So in this case now, water that was formed, water is liquid and not gas, so it cannot be considered as a residual gas. But if it was steam, that is, this was in the gaseous state, you would have had to like combine both of them together. And so that's the basic idea of stoichiometry. That's the basic idea of stoichiometry. Once you understand this, then you don't have any problem. Now, if you want to look at how to solve more difficult problem, you can see the link pop up. There's another video attached where you can see a solution to more difficult problem. And if you also have any difficulty understanding any part of this video, just let me know in the comment. And if you have not subscribed to the channel yet, this is the right time to do so. Make sure you do that and like, and make sure you share as well. So before I finish this class, I'm going to talk about one last thing, which is talking about theoretical yield and actual yield. So there's something we call percentage yield. And percentage yield is always given as the actual yield. So percentage yield. By now you know that I am very, very bad at writing this percentage sign. So percentage yield is actual yield divided by theoretical yield multiplied by 100%. So what is actual yield? Actual yield is actually the what you did in the lab. So in your experiment, what you are able to get, and theoretical yield is what you intended, what you were supposed to get. If you are to do the normal computation, it's the maximum product that you are expecting to get during a reaction. But actual yield is the exact product that you are able to get during the reaction, maybe due to some things, one or two things or the other. So that's basically what stoichiometry is all about. So the first thing to do whenever you want to do anything under stoichiometry, you must first of all balance the equation. Balance the equation. Balance equations. Next is convert to moles. Convert to moles. Unless you are dealing with gases, then you can make it remain volume. You can make it remain volume. But if it is not in volume, if it is mass that is given, always convert to mole. Then once you're done with that, establish the mole ratio from the equation. Establish the mole ratio from the equation. Establish the mole ratio from the equation. Then the final thing you do is to determine your limiting reactant. Once you determine your limiting reactant, whatever number of mole that your limiting, whatever number of mole of your limiting reactant that is given, that is going to be what you will use to do every other calculation, because like I said, it determines the extent of a reaction. It determines the extent of a reaction. And that is it about stoichiometry. I'll see you in the next one.